I'm incredibly excited to introduce our symposium for today, which is on early intervention, finger counting, patterning, working memory, and number games. I can turn this over to Rebecca Bull, who's the symposium organizer, who can talk a little bit more about the goals of our symposium today.
Thanks, Andy, and hi from the central coast of New South Wales in Australia, where it's 11 o'clock at night. I'd like to start this meeting by acknowledging the traditional custodians of the land from where I join you today, and that's the Guringai people. And I'd like to pay my respect to the elders past, present, and emerging of the Guringai Nation, and extend that respect to other Indigenous people who are present with us today. So I'm very delighted to have 4 speakers today, representing all parts of the world. So we've got a speaker from Spain, from Belgium, from the US, and well, from Singapore, but originally from Spain. And what we're going to be doing today is presenting 4 talks, which are all interventions designed for use with preschoolers and primary school children. And they focus on different aspects of domain-specific and domain-general skills. But importantly, they're interventions that have been designed to be as ecologically valid as possible and potentially sustainable at wide scale for use by teachers, or potentially for use by teachers, so they can be implemented in the classroom during regular curriculum time. So what I'd like to do is hand over to the speakers. I've asked them all to speak for 10 to 12 minutes so that we have time for 1 question as we do a handover. But I think all of the questions we'll save to the end, when hopefully we've got 10 minutes or so to have some general questions or feedback. So without further ado, I'm going to hand over to Rosario, who is presenting on behalf of her colleagues from the University de Salamanca in Spain. So Rosario, I hand over to you.
Thank you very much, Rebecca. Well, I'm going to share my presentation now. Are you seeing the presentation?
Yes.
Okay, perfect. Thank you very much. Well, good afternoon from here, from Spain. First of all, I would like to thank all of you for being here today, and I will present on behalf of Professor Orrantia, who was unable of being here today, and the title of our presentation is The Role of Fingers as a Medium to Support Children's Understanding of Cardinality. Well, by the course of this presentation, we are going to try and answer some questions. And the first question is, why did we decide to look at fingers? Well, we focus our research in the role of fingers in the acquisition of cardinality for 2 main reasons. Because learning the cardinal meaning of number is a crucial milestone in early numerical skills, and because it has been shown that preschoolers' understanding of cardinality is predictive of later mathematics achievement. So we wanted to focus not only in the acquisition of cardinality, but also in what can be done to support this process. In this sense, there are mostly 2 lines of studies that have been conducted. On one hand, it is thought that when counting and labeling are used together, facilitates children learning of the cardinal principle. And on the other hand, some studies have focused on the role of fingers and gestures. In this topic, there are 2 main lines of research. On one side, some studies have proved that pointing while counting help children because they can keep track of counted items and coordinate the one-to-one correspondence between the number words and the object counted. And on the other hand, some studies have shown that finger patterns may play a functional role in numerical development by facilitating the connection between quantities and number words. Nevertheless, there is no empirical evidence that finger patterns do support the acquisition of the cardinal principle, and that is exactly what we aim to study. And that leads us to our second question. How did we develop our research? Well, for this purpose, we designed a pre-test, training, and post-test with 51 children enrolled in the first year of preschool education that had not received mathematical instruction. In the pre-test, children were tested individually. The training was carried out during 15 sessions in a big group, and the post-test took also place individually. And regarding to the tasks, 5 different tasks were used. And these 2 tasks were also used in the post-test. First of all, to evaluate the understanding of cardinality, we used the give a number task. And in this task, children were given 15 small balls, and they were asked to give exactly a number of balls, beginning with 1 ball and finishing with 10 balls. The highest number of balls that children were able to give to the experimenter in 2 or 3 attempts was coded as their knower level. So we classified children in 3 different groups: 1, 2, and 3 knowers, those who were able to give 1, 2, or 3 balls; 4 knowers, those who were able to give 4 balls; and cardinal principle knowers, those who were able to give 5 or more balls. We also used 2 tasks of pattern recognition with finger and with dots. In the finger pattern recognition task, children were asked to indicate the number of fingers raised in a picture with a handshake from 1 to 5. And in the dot pattern task, children saw also patterns from 1 to 5, but in this case, dots were arranged like those on dices. And we also used 3 more tasks as a control measure to be able to compare if there were any difference between groups in the pre-test. For this reason, we use knowledge of the counting list, a task of visual working memory, and a task of fine motor skills. And regarding to the training, children were classified in 2 different conditions. Condition 1, label and count, and condition 2, finger patterns. But the structure of both conditions were the same. Each session started with a song related to numbers from 1 to 5. The only difference was that in the first condition, they only set the number word, and in the second condition, they associated the number word with a finger pattern, for example, 2. And after that, a counting activity with flashcards was done. In the first condition, children had to associate some quantities with the number words. And in the second condition, the same process was enriched with finger patterns. Moreover, it is important to highlight that both training protocols were executed in a real-life environment. That is, the classroom teachers were instructed to conduct the training in their daily life activities. So now that we know the training, you will be wondering what happened after this training. Well, first of all, in a preliminary analysis, we could check that there was no differences between groups, between those assigned to the label and count condition and those assigned to the finger pattern condition in the pre-test. But what happened in the post-test? Well, in this slide, you can see the label and count condition on the left and the finger pattern condition on the right. First of all, in an analysis of variance, we could check that children in the finger pattern condition outperformed those in the label and count condition. And then we checked the transition of children in cardinality between the pre-test and the post-test. Here in red, you can see 1, 2, and 3 knowers, in yellow, 4 knowers, and in blue, cardinal principal knowers. And in the label and count condition, as you can see here, a total of 53% of the children transitioned to 4 knowers or to CP knowers. Whereas in the finger pattern condition, a total of 79% of the children transition to 4 knowers or to CP knowers. And what is more, at the end, here in the label and count condition, half of the children were still 1, 2, or 3 knowers, but in the label and in the finger pattern condition, 64% of the children were CP knowers. So,
Oh,
in conclusion, what did we learn? Well, our results show that children assigned to the finger pattern condition outperform those who received the count and label instruction. And this finding provides evidence that children grasping of a cardinality principle can be effectively supported and even accelerated early in development. But why finger patterns may contribute to cardinality learning? Well, because they possess the symbolic properties of number words, but they also have iconic properties preserving cardinality. For example, in these 2 pictures, we can count together 1, 2, 3, 4, 5 items in each of the pictures. So finger patterns could serve as a bridge between cardinal labels of number words and the site of the set resulting from the count. For this reason, finger patterns could be a great tool to use in classroom and to help children to understand cardinality. And that's all for me. Thank you very much.
Thank you, Rosario. That was a really excellent talk. Can I ask if anybody has a quick question for Rosario that they would like to give? Andy, if you could help me have a look around the participants for any questions.
Yeah, absolutely. If anyone wants to identify themselves by either typing in the chat their question or their that they have a question, then we can call on them and spotlight them. Or they can just speak up and if we have fewer questions, we can always leave some time for discussion and questions at the end too.
Yeah.
Looks like Bert has a question there.
So Bert's saying, did you see any effects on the other outcome measures?
Sorry, Rebecca?
Bert is asking if you saw any effects on the other outcome measures.
Well, in the no, we didn't see anything.
Do you think that there would be any long-term effects on other outcome measures if it's helping children to gain cardinality at an earlier age?
What we think that this is because we caught children in an early age, so this can help them in this process when they hadn't acquired cardinality yet, but maybe later we had it was different, the effect that we
Sorry, somebody cut in there. I don't know if anybody else had a question just now.
Looks like there was just one other question as to whether this has been published yet.
No, it's in evaluation.
Great, thank you.
Thank you.
Okay, well, if anybody else has any other questions, we'll save that for the end, or you can put your question in the chat. So I think now we'll hand over to Nore from KU Leuven in Belgium. So Nore, over to you.
Okay, thank you. I'm going to share my screen. Okay, so hello everybody. My name is Nora from the University of Leuven, and I'm very happy that I'm able to present to you my intervention on patterning in 5-year-old children. So as you are probably aware of, early mathematical ability is a broad concept that covers a wide range of abilities, but most research so far has been looking into numerical skills, and we, in my PhD project, start to look into another aspect of early mathematical ability, namely patterning, which has recently been gaining more and more attention as an important aspect of early mathematical ability that is also related to later mathematical skills, even above prior numerical ability. And the present study had two main aims. First of all, we were looking into how we could stimulate young children's patterning ability already in preschool. And second of all, we were interested in whether there was also a causal association between patterning and numerical ability. So in other words, whether our intervention on early patterning would also have an effect on numerical ability. So concerning our first aim, it is also important to have a look at what is currently already happening to stimulate or support patterning understanding in early childhood. And I think the two examples that are given here on the slide are probably very common or familiar for most of you, at least in Flanders, but researchers all over the world have reported this. Main focus is on activities that are shown here, in which children are required to extend repeating patterns, either on worksheets or with concrete materials. However, many researchers and mathematicians have been criticizing these kind of activities for two main reasons. First of all, these activities do not really focus on the structure of the pattern, which in case of a repeating pattern is the unit that is repeated. And this is what makes a pattern mathematically valuable, because this unit can be used to predict how the pattern continues and makes a pattern not just a random sequence, but really a pattern. A second problem is the main focus on repeating patterns and even very basic A-B patterns, thereby neglecting other kinds of patterns such as growing patterns. Number sequences, which are also growing patterns, are often only introduced in primary school, but there are also growing patterns without number symbols that might be feasible or that are feasible for preschoolers, like the example you can see on the slide. And in this case, there's also a constant increase in the number of objects, in this case, the blue triangle. Concerning our second aim, the transfer to numeracy, we were interested in this causal association, not just because both patterning and numerical ability are aspects of mathematical ability. Associations have already been found, but it is also important to know whether stimulating these early patterning skills would transfer towards numeracy. And why do we think there might be such an association? Because the structure that can be found both in repeating patterns, so the unit, and in growing patterns, this constant increase or decrease, can also be found in many numbers in our number system and in quantities. So for example, the most typical one is our base 10 system, in which the units and the tens repeat over and over. And of course, there's also a constant increase or a constant association between two consecutive numbers. Another example, if we start counting in steps or counting objects in small groups, we make units. And this leads to a counting sequence in which there is also each time 2 more, so a constant increase in the number. And this idea, understanding these structures within numbers and quantities, might support children's understanding and their numerical ability more generally. What did we do in the present study? We did a pre-test, post-test study with a control group. There were about 70 children in both groups. And the control group was drawn from a larger longitudinal study, whereas the patterning group consists of children that went to the same schools, had the same set of teachers, but were from a different cohort. These children were 1 year younger than the children from the control group, but they had the same school setting. So we went back to the same schools 1 year later. We trained the teachers to give the intervention, and we had the same task at pre and post test. The tasks that were administered at pre and post test assessed both their patterning ability and their numerical ability. Numerical ability was covered by means of a range of tasks, which I think are familiar to most of you, including counting, symbolic and non-symbolic comparison, number order, and so on. The patterning tasks are shown here on this slide. So we had 3 kinds of activities, both for repeating and for growing patterns. In the extending task, children were asked to indicate a correct extension of the pattern. In the translating task, they were asked to copy the pattern with different materials. And in the identification task, they had to correctly memorize the pattern by when it was out of sight, in order to show that they correctly identified the structure of the pattern. What did we do during our intervention? So as I mentioned before, the teachers presented the intervention themselves during 30 minutes per week. This consisted of both whole classroom instruction, but also individual activities. And this was done during 2 sets of 10 weeks, with 1 set focusing on repeating patterns and 1 set focusing on growing patterns. I've put here a few pictures of examples of the part on repeating patterns. So as you can see on the left side on the top, this is one of the first lessons in which children were already confronted with this concept of a unit of repeat. Children could make their own repeating pattern, but they first had to indicate the unit that they would use, and then they could create the pattern. Below, you can see that we also learned the children to use abstract labels to name the patterns. So in this case, we use letters, and children were required to match the pattern with the name, so AB, ABC, AAB, or ABB patterns. On the right-hand side, you can see the pattern monster that was introduced to make the distinction, or to learn them make the distinction between a pattern and a random sequence. This was again based on the idea of a unit, whether there was a unit of repeat or not. The monster was there because he had shuffled some of the patterns into random sequences. So they had to sort it either with a monster or with Mr. Pattern, which was our mascot of the intervention. So of course, the most important question, what was the result of this intervention? So first of all, it is important to note that we found no differences between the control group and the patterning group at pretest on any of the measures. So not on patterning, but also not on numerical ability. At post-test, first for patterning, we found significant differences in favor of the patterning group. So the intervention was effective for both patterning abilities, with a small effect for repeating patterns and a medium effect for growing patterns. Regarding numerical ability, we were not able to find significant differences between the 2 conditions. So what can we conclude from all this? Regarding our first aim, the stimulation of 5-year-olds' repeating and growing patterning ability, I think we can say that this focus on the structures seems effective for both repeating and growing patterning ability, and that we can also already stimulate these very young children, only 5-year-olds, growing patterning ability. Regarding our second aim, we were not able to find any support for a causal association between patterning and numerical ability. It is possible that some part of the association that has already been found between patterning and numerical ability is explained by a third variable. One variable that might be important there is spatial skills, which have been associated both with patterning and numerical ability before. It is also possible that a causal association was actually or could be found if we combined such a patterning instruction with a numeracy instruction in which these structures are made more explicit. So as I mentioned before, with accounting in groups or the base 10 system, if these are made more explicit. And yeah, one final aspect that might have obscured any causal association was the fact that we had a business as usual control group that was drawn from another study. So we only have limited information on what happened regarding the numeracy instruction in the control group versus the intervention group. And a next step would be to really compare in a classroom the impact of a numeracy instruction versus a patterning or instruction. So thank you very much. That was it for me, and I'm happy to answer any questions.
Thank you very much, Nore. So again, I'll open it up if anybody has a question they want to ask, either jump in or just flag yourself up as wanting to ask a question. Andy, if you could help me monitor again.
Nore, I have a question. It's Anna.
Yep.
Hi. Hi. It's so interesting. Thank you for this. So as a person who's not expert in the patterning literature, my read on the findings is that there's been kind of conflicted findings. It's not as clear as maybe some other elements of things that might contribute to numeracy. So yeah, I guess I'm curious, like, what do you think the future is of integrating patterning into early childhood curricula, because it does seem, at least in the US, to be a major focus for teachers?
Yeah, thank you for your question. I think one important issue, first of all, is to look at what is happening so far, because when I look in Flanders, it is not at all the case that there's a huge focus on patterning. And I don't know how the situation is in the US, but based on what I read, there is this criticism about the quality of the type of patterning instruction that is provided. I think one important thing is, for sure, we could not find an effect on numeracy or numerical ability as we measured it, but I don't think that this means that patterning is not relevant for mathematics overall, because mathematics is broader than numeracy. So I'm still convinced that this patterning is valuable, but I also do think that there is some potential in these patterns to be related to numbers and numeracy instruction that is maybe not being used so far. So it's maybe something we could explore, whether understanding these, whether we could exploit, I think, better these patterns to be used to support numeracy as well. So I hope that answers somehow your question.
Yeah, no, thank you, definitely.
Thanks a lot, Nore. I think there's a few more questions in the chat if you want to take a look at those. But we can perhaps move on to the next speaker to keep us to time, and I'll let you take a look at those additional questions. So our next speaker today is Anna Shusterman from Wesleyan University. So I'm going to hand over to you, Anna.
Thank you. So let me share my screen here. Sorry, I'm always so slow at this. Okay, so this talk is a little bit different because we don't have a ton of data. We have pilot data to suggest that these kinds of interventions that I'm going to talk about are good. But what I don't have is good data. That's what we're working on. And what basically, just to give a very broad sweep of what we're trying to do, is we're trying to take the kind of research that Rosario and Nore just presented, right, where we have these nice experimentally assigned conditions and things that we have theoretically motivated to potentially have an impact on cardinality. And try to figure out how to actually put them into schools, because the truth is we do have decades of things that cognitive development researchers think should work, and at least in the American context, they're not being utilized in schools at all. And it's not for lack of curricula existing. So there's curricula that exist that have been funded by millions of dollars from educational institutions and the National Science Foundation, and it's not even for lack of preschools purchasing those curricula. So they're created, they're researched, they're purchased, they're high efficacy, and for whatever reason, they're not being utilized. And so that implementation gap is kind of where we've been playing. So I think we have some common agreements here, and there's lots of citations for each of these claims. Math is undertaught in most preschool settings. That's definitely true in the United States, and I think it's true in a lot of places, probably not globally. I'm really appreciative of being in this very international symposium. Another common agreement, I think, is that preschoolers are ready for and enjoy learning math. And the third common agreement is that preschool teachers could use some more support and concrete resources. This is the number one thing that comes out if you actually ask teachers directly, what do you need to increase teaching of math in your classroom? What they need is more materials. So the point is that if it were easy, we would have done it by now. And so what we need to understand are the barriers to implementation. And there's been a variety of hypotheses, some of them described by people who I see in the audience. So a possibility is that maybe teachers don't totally understand the developmental trajectories in early numeracy, so they're not positioned to support them. Another possibility is that they don't have materials that align well with the cognitive development research. It's based on sort of intuitive theories of math development that is not really supported by research. Another possibility that is not on this list on this slide is that preschool teachers have a lot of math anxiety, and that's what's holding them back from teaching it. And interestingly, we poked at that hypothesis less by giving them math anxiety surveys, which other people have done, and just by asking them. And in fact, what they express is a lot of positive affect around math and a lot of enthusiasm for the idea of teaching it, and a lot of complaints about lack of training in their training programs and lack of materials or professional development about how to do it. And a sense that the materials that they are given are boring, fail to engage the children, and therefore become really aversive to use if what you're trying to do is create a really stimulating, intellectually lively, and positive affect kind of classroom. And then a fourth possibility is that the curricula that that exist fail to fit within the existing structure and format of preschool. So preschool, in contrast to more formal grade schools, tends to be much more free-flowing. If it's warm outside, you might spend more time outside. If it's raining, you might spend more time inside. Children have moods. Those moods are sometimes contagious. Maybe one day is better to do a more formal lesson. Maybe one day is worse to do a more formal lesson. Sometimes the energy is high, and like a quiet, focused math activity is not what you're going for. But the curricula that exist are like, on Monday you do this, on Tuesday you do this, on Wednesday you do this. And so I don't think it's too hard to observe mismatch between what the reality is of most early childhood settings and for teachers to use. And so what ends up happening in an interview project that a student of mine, Angela Lowe, did, is that teachers report using the curriculum, but kind of like a cookbook. So they like to use a very mix and match approach, and it doesn't scaffold with any developmental trajectories that we know about in early numeracy. And so it ends up being like a little bit random to check the box, we did some math. And so the question is, can we do this better? And also to say that it's not necessarily easy, because if it were, we would have done it better by now. And so the proposal is that the problem is not really with the teachers. Like, we could do a math anxiety intervention, we could do other PDs, but when you talk to teachers, that's not what they say they need. And so in the interest of kind of honoring that voice and that perspective, we should notice that we fail to give them what they need. So what is needed? You know, I've had many generations of students and teachers kind of go through conversations, and we come up with a fairly stable list of factors that people are looking for. The activities first all have to be fun and engaging. They have to be flexible, so they have to work with an individual or a full group or a small group. They have to be varied in duration. You have to be able to do them in any order, because that's the reality of how teachers will use these curricula. They have to respect teachers' autonomy, right? So preschool teachers, like, it's a very hard job, particularly in the US, where it's really undercompensated. And so, like, the one thing you get to do is design your classroom and your lessons. And so I think it's important to maintain that. They have to be easy to differentiate for different levels, because children are at really different levels when they're age 3 and 4. They have to be, I think, open-ended to invite continued play. So if they stop play because you got to the right answer, then they're not inviting that kind of numeracy experience that we want. That's one of the few things, like, I guess along with finger counting, I've learned this morning that we know promotes cardinality. There's very few things we know for sure promote cardinality. Time and experience with math is one thing that we know for sure. It sounds like finger counting is another thing we maybe know for sure, but there's not a lot of other things. So we do have to be giving kids that time. It should be connected to the research, and it should be child friendly. I would also add that I think in honoring the other dimensions of children's intellect, they should be beautiful, they should be imaginative, they should be varied, right? They should not be ham-handed, like in a way that something might be appropriate for a research study to figure out if an intervention or a theoretical construct is the right one to attack. That might not be the exact intervention that we might want to put into a school, because it's not fun enough or beautiful enough or varied enough or open-ended enough. So we have to maybe make some moves from what we know about the interventions to that. So we've been working for a number of years on making these kinds of math games. Here's just some images of some of the more successful ones. And what I mean by successful is if you leave them on the shelf after introducing them to children, they will go to the shelf and play them by themselves. For me, that's the mark of a successful math game. And most classrooms that we work in don't have games like that support math concepts. So Math Garage, you have like little cars that you park, and there's dots. Panda Palace is a lovely book by Stephanie Kalmanson, where there's different animals and they all have to get seated at the table. And there's like 1 elephant and 2 lions and 7 penguins, and they all have to get seated at different tables. So we have cutouts that are that they kind of act out. Children will read this book over and over again and act it out over and over again. And then we have Monster Math, where the little boots are set far away from the monsters, and children have to leave the monsters in place and go fetch boots. So it's kind of like a spontaneous focus on numerosity test. Like, do they attend to the quantity? And you don't say how many feet are there, and you don't say how many boots are there. You just kind of let them continue to discover the answer to that. So the games have been developed over a number of years. Children like them when we put them into preschool settings in a month or 2-month intervention in the control conditions, and these are admittedly very small, like just a few classrooms control and a few classrooms with treatment. The control classrooms always show 0 growth in our little pilot studies, and the math games are better than that, which I think is kind of unsurprising. but then we have these questions of implementation. As we've tried to standardize them to try to give them to teachers, we don't really know how the preschool materials should be introduced. But that is probably as important as the materials themselves, because like I said, there's a lot of other well-validated, efficacious math curricula for preschool that nobody's using. So unless they're forced to by a district director. So the principle of these games, of course, is within the framework of guided play, and guided play is a little bit different from free play, right? So all play, we think, can support learning, gives the child agency, comes with positive affect and some sort of intrinsic reward and motivation. Guided play is a little bit funky, right? Because the adult will have a learning goal in mind, like we want to get you towards numeracy, which there's definitely a clear tension with the goal-free nature of real play. And there's a lovely quote called chocolate-covered broccoli. Like, we don't want the guided play interactions to feel like chocolate-covered broccoli. The adult structures, the experience and language is often seen as important for scaffolding the learning process. So, so the sticking point for implementation is how playful should we be? How much should the child direct? How open-ended should adults' questions be? How much commitment to a learning outcome should the adult have when implementing math games in a single episode? Because we know from all of our studies that these numeracy concepts take years to develop. So what are we really going to do with one instantiation of a math game? And so that's what we're doing. So this was like a theoretical talk to set up a study that we're just embarking on, where we're experimentally varying levels of guidance. So in Math Garage, for example, low guidance condition would be, can you park these cars? In high guidance, it might be, can you match the car number to the dots? The cars all have little racing numbers on the back. We're also varying whether undergraduate math ambassadors go in and implement these things, or preschool teachers, to try to figure out really what's the best implementation that most easily flows these things into a classroom. So that's it. I want to thank many generations of our translational research workshop class, about 8 generations, including Andy Ribner, who's organizing our beautiful symposium. So I'm very proud of his contributions to this project, and also to MCLS and our long-term collaborating schools and teachers. So thank you, and I will take any questions.
Thanks, Anna. Does anybody have a question for Anna? There is one question, I think, for you in the chat, Anna, from Elizabeth Henning.
Yeah. I do think that there is something, right, there's something very important about games when we think about the negative affect that many children start to bring towards math, right? Like, maybe games are a way to bypass or avoid that by really thinking harder about how do we make the learning strong and rigorous, and the affect positive, joyful, with intrinsic motivation, and all of those good things.
Thank you very much. Maybe I could just mention that what I've been reading lately, and which has really made a big impression on our work here in the southern part of the globe, is so-called playful learning, which, you know, people like Mitch Resnick and others who work with and for Lego would like to couch in a somewhat different way than what you do. And just in principle, without going on too long, I want to say I support your view. Thank you.
Can I just ask one follow-up, which is what is the main contrast between their view? Because I'm not familiar with it, but I will look it up.
I think yours are based in the ground, the very ground, the trenches of early learning, and it has very little to do with the material world. So it seems to me the objects that you do bring into the material world, like objects with which to play and to create and to think, that those are really much more grounded than some of the other views, which are grounded, but grounded in the, yeah, how shall I say it, in the epistemology of a major international foundation and maker of playthings. Okay, I think I've said enough.
Yes, that's so helpful. Thank you very much.
And I think, Anna, your ideas of guided play overlap quite well with the notion of purposeful play that they have in Singapore. Again, kind of teacher guided with an objective in mind for the learning.
Yeah, I agree, and we look at it, and I guess just the I guess I just want to, the theoretical argument, right? The thesis of this talk is that we have this lovely idea of guided play, but we haven't operationalized it at all. Like, in fact, if we try to make guided play instructions for all of these games we have no idea which instructions are in that, where they fall in that spectrum, and that we have a lot more work to do, I think, in that spectrum.
Yeah, great. Thanks a lot, Anna. So again, just leave any additional questions you might have in the chat, and I'll leave Anna to take a look at that. And we'll move on to our last speaker today, which is David Munez from the National Institute of Education in Singapore. So David, I can't see where you are on my screen, but I'm going to hand over to you.
Okay. Hi, Rebecca. Can you hear me?
Yes, we can.
Hello? Okay, great. Just let me share my screen. Okay. Well, first of all, good evening, everyone from Singapore, and thanks, Rebecca and Andy, for organizing this. I will try to get this done in less than 10 minutes, so we have some time for discussion. I'm going to present some findings regarding a study. I'm sorry, I don't know why this is running so fast. I'm going to present some findings regarding a study. I'm sorry, something is wrong with my screen. Okay. Okay. Can you see my screen now?
Yes, we can see your third slide, David.
Okay, yes. Okay, great, I'm sorry. Okay, so these are some results of a study with children in the learning support for math here in Singapore. And I will try to go briefly over the introduction, and then I will discuss the challenges and limitations that researchers may face when they try to implement or translate findings from the lab into real learning environments. Okay, sorry, please. There is increasing interest in math learning difficulties and how we can support the students with or at risk of math learning difficulties. This is not new, but it has been boosted by findings that track these deficits back to early childhood and connect these deficits in math with a variety of domains. For instance, we know that particular cognitive deficits in core number knowledge or memory retrieval relate to math difficulties. Among these cognitive correlates, working memory or updating capacity has been given a leading role. For instance, working memory explains a substantial part of the variance in math achievement over the school years, and it's involving several math skills such as arithmetic word problem or solving algebra problems. For instance, when we try to solve a word problem, we have to retrieve information from memory, as well as to update that information with new incoming elements from the text of the problem. Similarly, another aspect that has attracted a good deal of attention is our capacity to process in basic numerical information. So this information does not relate to arithmetic or algebra knowledge or any other math ability that can be learned at the school. Early numeracy skills such as, for instance, number line estimation or numerical discrimination are known to play a relevant role in early childhood mathematics and contribute to substantial variation in more advanced math skills at the onset of formal education. Furthermore, we have evidence that these skills also have diagnostic properties in the sense that they may provide thresholds for identifying future math learning disabilities. This interest in math learning difficulties is also reflected in an increasing number of intervention programs that have been addressed at children with math learning difficulties. Although different categorizations have been suggested, I say that we can distinguish between programs that focus on domain general aspects, such as working memory, updating capacity, and those that focus on numerical aspects. But we have some outstanding issues in the literature. So the review of the literature shows mixed findings regarding the effectiveness of these programs. Some of the issues are, for instance, that we have different types of populations, different developmental stages, treatment effects, and math outcomes. But there are also issues regarding the characteristics of the interventions or the potential moderators of the effect of intervention programs. For instance, individualized interventions or one-to-one administration in which the experimenter guides and supports the training are thought to be more effective. Another issue that is more relevant, and this is linked to Anna's talk, is that actual intervention programs involve a small number of participants, which affects the power to detect significant effects, and that actual intervention protocols cannot be implemented in regular classrooms as supporting tools for teachers. For instance, they require one-to-one administration or rely on long training periods, which does not align with the dynamics and activities of a regular school day. If we can say a regular school day, of course, if it's raining, then they will change the activities and so on. So for an intervention to be effectively implemented in a real learning environment, the training periods should be short but frequent, and the demands on the teachers should be close to zero because they cannot actually administer the intervention, at least at this scale. In the current study, it's a large-scale implementation of a training program to support teaching efforts in the learning support for math. And the study included more than 400 kids and 63 schools, and it was conceptualized as a computerized game-based training where the cognitive requirements of the games varied as a function of each child's capacities. We included 3 experimental training conditions and an active group. And the protocol was designed as a one-year gaming experience, and the training periods were short but frequent. We had a variety of measures, working memory, math measures, and numeracy, and basic numeracy skills also. We have 4 data points and a delayed post-test 6 months later, and the study spanned 18 months. In order to analyze all this data, we formulated a growth model to investigate the effectiveness of the treatment conditions, and we computed a separate model for each dependent variable. So I will not spend time on this. Just want to clarify a few things. The first one is that this particular approach allows investigating the trajectory and shape of the growth curve of children allocated to the active control condition. And this is important because it provides insights into long-term effects. For instance, it may be that long-term attenuations of the effect of interventions may simply correspond to a normal deceleration. And we also specified in this analysis a baseline treatment interaction to understand for whom the intervention was effective, because it has been suggested that, for instance, children with limited skills may benefit more from the training as they have more room for growth. The results, these are just the means and the standard deviations. As you can see, there is not a linear trajectory, it's more like a quadratic trajectory or something like that. So I will go briefly over this. We found that, for instance, constraining the intercept of the growth curve to equality across treatment groups improved the fit of the model. And this indicates that there were no differences between treatment conditions when the intervention was rolled out, which is good. But we also found that children allocated to the numeric working memory training and numeric condition showed better number-line estimation skills at the end of the study. This is the growth curve for number-line, and it can be seen that deceleration as the average percentage of accuracy error becomes smaller and smaller. And this also confirms that the treatment effects are not permanent in the sense that the difference between the active control and the experimental average trajectories do not keep increasing over time. For instance, whereas differences are observed in this graph, those differences will probably vanish over time since there is no room for improvement in the long term. We also find significant differences in game exposure or game experience. So although children were allowed to play the games for about 6 hours, which is significantly less than the 24 hours of gaming time that we had planned, we found that children in the working memory training conditions barely completed 20 or 30% of the games, whereas children in the numeric condition completed about 60% of the games. And this suggests that these children suffer from cognitive load or found the working memory training challenging and cognitive demanding. So we included this variable in the model and conducted a conditional analysis. And we found that game experience had a role on all of the outcome variables. So results from the analysis revealed that at the median level of game experience for each treatment condition, which is 20% more or less for numerical working memory and working memory, as you can see in the graph, and 60% for numeric training, the effects of the numeric working memory and numeric protocols on children's number line estimation skills remain more or less the same. But a significant treatment effect emerged with regards to other math skills that were, and this is important, were directly trained in the numeric protocol. I will explain this later. We also investigated the treatment based on interaction to test the possibility that children with limited working memory capacity or math skills had larger growth rates since there is more room for growth. However, we did not find evidence of this association. So how can we explain these findings? Well, first, I think that we add to those studies and research that suggests that working memory training may not be effective, at least not for everyone. And although some studies with adults have found that the effects of training may be more evident when there is a deficit of working memory capacity, our findings indicate that the outcome of such cognitive demanding programs may be limited if the cognitive resources are poor. In our study, for instance, the majority of children had really poor working memory capacity, which could probably increase the likelihood of cognitive overloading during the training, for instance. Second, we provide evidence that real-life implementations of intervention programs to support teaching efforts are challenging. So when interventions are applied in real-life settings, it's harder to control for training regime, including the quality, dose, and fidelity of its delivery. Indeed, the effectiveness of extant intervention programs is linked to administration formats that are hardly viable in a real classroom setting. For instance, teachers cannot simply spend 30 minutes with each student to monitor and administer the training. And indeed, teachers feel that interventions supported by experimental literature do not make sense or do not work in their classrooms. So the poor compliance of the current study also confers ecological validity to the study. For instance, among the reasons for poor compliance, teachers mention children's frequent absenteeism, limited curriculum time, the need to prioritize curriculum time against gaming time, and that some children, for instance, were not keen to play or struggle with basic games, such as, for instance, remembering the last 2 items from a list of 3 or 4 items. And finally, although we found some effects regarding the role of numeracy training, those effects were really, really small and related to improvements in conceptually similar tasks. For instance, numerical operations or math fluency, where these 2 tests, for instance, are testing addition and subtraction, which are pretty much the activities that we're training, part of the activities that we're trained in the numeric condition. And this has been found in other studies that have been focused on training particular numeracy skills. And calls, we think that calls for additional research regarding the role of domain-specific aspects on the acquisition of more advanced math skills over the school years, for instance. I'm gonna finish here because I don't have more time. So thank you very much.
Thanks, David. That was a lot to get in such a short amount of time. I think we have time for a quick question, if anybody would like to ask anything. David, I was wondering if you could just describe the difference between the different training conditions, because I'm not sure if it was clear what the difference was between the working memory versus numerical working memory conditions.
Yes, for instance, in the numeric working memory condition, we had magnitude comparison, both symbolic and non-symbolic. We also had some games with basic addition. For instance, you have 5 marbles and I'll give you 2 more marbles and you're gonna have 5 marbles. We also had some numerical discrimination games, basic numeracy skills, and addition and subtraction. In the numeric working and number line, And in the numeric working memory condition, we had pretty much the same activities, but included a numerical including a working memory component. So for instance, for the number line, we had the number line game. Children were shown the numbers encapsulated in a shape, for instance, in a circle. So number 6 was falling, and the children had to decide where on the number line the number 6 is. But then the working memory component was the next step of the game. It was like, what was the last number that was shown in a circle? And they had to indicate that it was a 6. So it was more complex or more challenging, but include both working memory training and numeracy training. And the working memory training was pretty much only working memory. So for instance, for number line, there were shapes falling, and the children only had to indicate where this shape or where this figure that is falling should go. They had to remember later in a recalling phase the last figure that was falling and things like that. And in the active control condition, they were playing games without numeric component and without training and without working memory component.
Thanks, David. That makes the differences a little clearer between the conditions. Well, I notice we're just over time now, so I don't know if anybody has a last question that they're just dying to ask, or whether we sign off here and let everybody get on with their day. Any last question? Okay. Well, I think do you see anything, Andy, or are we good to finish up?
I don't. I think it's time for you to go to sleep, as it's past midnight now.
It's the next day now.
Yes.
Yeah. Well, I just want to say thanks to everyone for joining us, and for to all of the speakers who gave really interesting talks today. Thanks a lot, guys, and hopefully we'll see you all in Dublin next year.
Thanks, everybody.
Okay. Thanks.
Thanks.
Bye.
Bye.